Good, you may start recording if you want and let me in. I hope my screen is visible to everybody. Okay. So good morning everybody again and welcome to the day 15 of the digital hardware design course using VHDL for 40 hours. If you people remember, in the last class we were discussing about the designing of counters and we came across different types of counters, right? Starting with the simple binary counters, synchronous counters, asynchronous counters. Then we have designed mod counters also. Then we have also discussed about the specialized counters like Johnson counter and ring counter. We have seen the designing as well as we have also seen the uh, working of all these counters, right? Simulation, done the verification and all these things. Following these sequential circuit designing, we have a new topic today that is called memory designing, right? And as I told you earlier when we started the synchronous designing topic, that in the synchronous design, a flip-flop or a latch is called the one-bit storage device. Okay. Following, when several flip-flops are joined together, they will become a register. And when these registers are stacked one upon each other in a specific pattern and will create in such an arrangement, then in that particular case, this stacking sometimes referred to as registers or register array. Okay. If we'll talk about computer architecture, processor designing, you have find out that there are small registers array are available in the form of cache memory, so to store the data. Apart from that, we have a different set of memories also, like primary memory, secondary memory in the computer system to store large amount of data. Okay, but in general, it will say memory is classified into two types. One is called RAM and another is called ROM. So in this particular course, we'll focus on these two memories. But apart from that, there are several other memory types are also there, like FIFO memory is there, first in, first out memory is there. Okay. Similarly, last in, first out memory is also there. Right. So, however, but in this course, we'll focus on the RAM and ROM designing only. Okay, how they work and how it can be how they can be designed. So, in short, what is a memory basically? Memory is nothing but it is a register array used to store the large amount of data in various electronic systems. In various electronic systems. In various electronic systems. Right? Types of memory, RAM and ROM. Who will tell what is RAM? Can anybody write in chat box? How can we define a RAM? Anybody of you, if you are listening, can you write something in chat box? What is RAM and what is ROM actually in one line? Anybody? Hmm. Computer short memory. It temporarily holds the data. RAM or ROM. So RAM is short memory that stores information for a small period of time. Very good. Very good, Shivansh and Shashank. So, yes, RAM is a temporary memory. And sometimes this memory is also referred as a, that's why, because it can store the data for a small period of time, it is also referred as volatile memory. What is the meaning of volatile memory? That is, it can hold the data, it can hold the data for a specific period of time, means it can hold the data, it can hold the data for a period of time as long as the power is on in the system. Okay, or otherwise the data would be lost once power is lost. As long as power is there, the data is there. If you want to that data to store again, then you need to sorry. If you want that data to data again, then you need to store it again. Okay, you need to again store in this multiple times. You can read and write with the RAM. RAM is called random access memory. Okay, so it is a semiconductor memory, very expensive. Okay, volatile memory can hold a data for a small period of time until the power is there. Otherwise, the power is, as power is off, the data is lost. Okay, as compared to that RAM, if we talk about uh, ROM, the ROM is non-volatile memory. Means it can hold the data forever. Once written, it can hold the data forever. Okay, it can hold the data forever. The data is, cannot be lost and not depends upon the power. It can hold the data forever. If you want to change the data, you need to go to manufacturer, right? Go to manufacturer and ask him to rewrite it. Okay, rewrite it because we cannot write it data in ROM because it is a read-only memory. In it we can write and read, but in it only we can only read. We cannot write anything. We need to go to the manufacturer and ask him to write the data for us so that we can read it or anybody else can read it as long as he want. And it is also The data is not lost when power is off. It is remains in it. Okay. So both these memories are used inside the computer systems, embedded devices, in electronic systems, right? And we are very much dependent upon that because the data on which we play, our mobile devices, embedded devices, computer system depends. It requires a memory, right? Without memory, the computer system, embedded devices cannot do anything. Okay, we need memories to hold the data so that we can work upon that then. So memory designing is always a concept and important concept and always into the picture. Okay. Now there are some variants of ROM nowadays. Okay, different variants of ROM comes where we can also have the ability, we can write the data also. Just like we have PROM, programmable read-only memory, UVP-ROM, ultraviolet read-only memory, then EVP-ROM, E-square PROM, electrically erasable programmable read-only memory. Nowadays, flash memories are there. Flash memories means the memories where we can read and write the data and store the data in ROM also. Just like your pen drives, your hard drives. Okay, so these are specific type of ROMs you can say, where we can store the data in a flash of seconds, and we need not to go to the manufacturer. So as per the latest technology, the ROM can be read and written also. Okay, but it depends upon the technology we are going to use inside the ROM, or you can say on which technology it is built upon. It totally depends upon that process. So ROMs are generally not costly. Okay, but RAMs are costly. RAMs are very much costlier. So that's why they are not being used everywhere. They are being that's why they are short memories and precious resources and available and have availability in a small capacity inside the embedded devices or computer system. Okay. Right. So let's start understanding RAM first. That how can we design the RAM? Okay, and then we'll talk about the ROM also. Random access memory, right? I'm assuming that I have this RAM. Let's say simple. Let's say this is a RAM. Each row is representing a register. You can say each row is representing a register. Okay, just like this. And let's make a simple design. Simple. Okay. So you can say this is row one, row zero, or row one. You can say, and I am assuming that this is nothing but this is a register. A one register one, register 2, register 3, register 4, register 5, register 6. Similarly, you can add upon more locations or more registers in it. As I told you, that memory is nothing but it is a stacking of registers only. It is a stacking of register. Okay, so this is register 0, this is register 1, this is register 2, 3, 4, 5, 6, 7, 8. So let's assume that we are having 8 registers. Okay, we are having 8 registers, and each register can hold 8 bit of data. For an example, each register can hold 8 bit of data. Okay, each register can hold 8 bit of data, right? So this is a 8-bit register, we can say. All are 8-bit register, let's say, so that they can store 8 bit of data, right? So that they can store 8 bit of data. 8-bit register, so they can store 8-bit register. Okay, 8 bit of data means every register can hold 8 bits. 8 bits this, 8 bit this, 8 bit this, 8 bit this, 8 bit this, and so on to so on. Okay, so I'm just removing that. In memory designing, these registers are called as locations. Okay, also these registers are nothing but they are referred as locations also, right? What we can do, we can read and write the data in these registers. For that, what we need, first of all, we need two signals. One I need one I need a write signal. Similarly, another I need a read signal. I need two signals. One is write, and other is read. You can make them active low or you can make them active high, depends upon it. So one is write signal and another is read signal. So that we can write the data whenever it is required and when we can read the data whenever it is required. Okay. Another thing that we need, the data lines, so that we can store the data through them. So there is one input which is called as data lines, right? Your data input, data input, the data lines कुछ भी बोल सकते हो. Any other thing we need in memory? Hmm. Anybody? Any other thing that I need? Data in is there, read signal is there, write signal is there. I will put the data and activate the write signal. The data is written. I will, if I want to read the data, I will read using this or anything else I required. Tell me, students, or is it enough? Tell me fast. Is there any student available or listening carefully? One signal that I want, data output also. Yes or no? Tell me. One signal that I want, that is data out also. Yes or no? Data in to write the data or data out to read the data. Yes, sir. Yes, sir is okay. But any other thing apart from this, you should want me to include in it, or you thought that there it should be there apart from these signals. Whenever we want to write the data, we'll put the data on data in, we'll activate write signal, data is written. Whenever want to read the data, we'll put activate read signal and read the data on data out. Yes. Select line. For what? We need select line for selecting the specific location or a register, we can say that whatever data that is present over here, where it should be written. This is the use of memory. Otherwise, if there is no selection or no address that where we want to store the data out of these 8 registers, then this data will be written in all the registers, same data, which is of no use. We want the data should be stored here, similar data stored, not stored different here data over here. Okay, yes, to locate the memory of data. Very good, Srishti. So we need one more signal. What we can say, we need one more signal that is called address line. Sometimes it's called as address lines. How many address lines are there? Means the what is the width of the address line should be there in order to identify these 8 registers. And what should be the width of data input line and data output line in order to write the data or in order to read the data. This is another question now. Who will tell what is the width of data input and data output and what is the width of the address line and on which factor this width depend? Please tell. Tell fast. Suppose I have created a line over here. Okay, and I am assuming that this is a register. Okay, or should I write like this? Okay, I should do it like this. Wait. Uh, okay. Let me create another table of this size. Okay. Tell me fast. I'm waiting. What should be the width of data lines and what should be the width of address lines? This you need to give answer. Tell fast. Tell fast. What should be the width of address line and what should be the width of data line? Don't know? Not getting? Not coming into your mind? Okay, let me let me give you the answer. Okay, somebody have responded finally. Hmm. And data lines for n bits of information to be stored. Very good. So how many there? How many data lines should be required in it? Very good. We need 8 data lines because I already told you that the width of the register are of 8 bit. I have just previously mentioned that the width of the register is or location is 8 bit. So what we want, or at a time we know we can only store 8 bit of data, or in other words we can store 8 bit of data in one location. Okay, so what we need data lines of we need data lines of 8 bit, right? We need data lines of 8 bit. Whether it is a data input line, either we can write the 8 bit data or we can read the 8 bit data. What is the width of address line? Now tell, what is the width of address line? Yeah, it is okay that this is of 8 bit for this example, and it is also of 8 bit because we have taken the width as 8 bit. And for this example, what should be the width of address line? On which factor it depends? The number of bits used to define the memory location. That means how many memory locations are there? 8. In this case, there are 1, 2, 3, 4, 5, 6, 7, 8. 8 memory locations are there. So how many bits are required to define them? For 8 memory locations, we need not 8 bits. 8 bits, using 8 bits, we can define 2 to the power 8. So many locations. For defining for defining locations, 8 address to 8 locations, we can use only 3 bits. Yes or no? Because using 3 bits, right? Okay, we can use 3 bits. Let's see. So address lines, let's say if their address lines are M, right? So we need, if we want to calculate the address lines, okay, not M, I should write. If I need to calculate address lines, then it should be 2 to the power Generally, memory capacity can be defined as m into n, right? When we talk about memory capacity, it is defined as m into n, where m refers as number of registers or locations. Okay, number of registers or locations. This is memory capacity, right? Similarly, n stands for the data stored, yeah, the data that can be stored in one location. Okay, the data that can be stored in one location. So if I want to identify the capacity of this memory, so there are eight locations. There are eight locations, and each location can store 8 bit of data. So the capacity of memory is like this: 8 into 8, yeah, 8 cross 8. So it can store 8 8 ja, how many bits? I can say 64 bits of data, or I can say 8 bytes of data, because 8 bits means 1 byte. So total number of 8 bytes. So 8 bytes of data. So this is a 8 byte memory. I am creating a 8 byte memory. 8 byte memory means it can hold this much of bits, 8 cross 8, and memory capacity is recognized this. So if I want to identify the address lines, how many address lines are required? So the formula for address lines is m equals to 2 to the power superscript. If I would should use uh, I should write I should write like this: 2 to the power. I am using this sign. Let's say 2 to the power address lines. Okay, so m is here 8, and if I want to calculate address lines, so it should match this identity: 2 to the power 2 to the power 3 only satisfy this identity. So 3 is the address lines. Our address lines would be 3. Okay, right? And data lines would be 8. And how the address varies? Using 3 address lines, we can create 7 addresses. Okay, from starting from 000, 8 addresses, sorry, 0001, then 010, then 011, 100, 101, 110, and finally 111, right? So every location or every register is identified by a unique address. This is very important. Every location or every register is having a unique address, which can be either done in binary coding or can be used hexadecimal coding depending upon your requirement. But the number of address lines that we require, that is 3 in this particular case, and this is the generalized idea to identify the number of address. Okay, Dear students, have you got this? What I'm trying to say to you? Tell me yes or no, or any doubt you have till now. If you have understood this concept, please say yes so that I can proceed further. Okay, thank you. Right. So how it works? Working of memory. How it works? How it works? Whenever you want to write some data, okay, what you will do first? You should have the data on the data input line, and you should have a valid valid read write signal over here. So when you are writing, you should have to disable read because both these things cannot be done at the same instance of time. Either you can write the data or you can read the data. Okay, so put the data over here, put the required address over here where you want to write out of this, and then assert a write signal, valid write signal. Then after that, data would be written inside that location. Okay, so let us and to overall to synchronize all these things, we further need two more signals. Okay, which we have left out. That is what are these two signals? Clock and clock and reset. So let's draw that them also. One is clock, let's say. Another is called, let's say, reset. Let's say I have written RST in short form. Okay, so let's understand how it works. What should we do? If reset equal to 1 means everything should be reset. Means all the registers should be reset. So nothing should be available at data out. है ना? So memory clear, all memory locations, all memory locations clear. So for that, what I assume, let's take a variable कि जब reset 1 हो, some variable we have taken u, which is representing this complete memory, and it is getting its all location will getting 0 0 0 0 0 0 0. Let's say this variable is this type, that is all location will get this value, 8-bit data. Okay, right? Initially. After that, let's say I am saying that it is a memory variable. If otherwise, if reset is not 1 and you have applied a valid clock signal, say if clock is 1 and if you have applied a valid clock signal, else if you have applied a valid clock signal, okay, and in this valid clock, if your write signal is enabled and your read signal is disabled, right? Then depending upon your case, your address lines, depending upon your address lines, whether it is 00, 01, 001, 010, whatever the address lines you will write. Okay, let's say ADDR address lines is, है ना? You can store the data into a specified memory location. Data in, right? That memory location will get this data. I hope you will get my point, what I am trying to say to you, right? Initially, you will put reset equal to 1. All memory location will be resetted. After that, make this reset signal disabled. Put clock signal, valid clock signal. After that, put data on the data line. Let's say you have put some data. Let's say, for an example, you have put some data, uh, 0. Let's say you have put some data. Let's say, uh, for an example, 0, 0, 0, 1, 0, 1, 0, 1. Let's say this data you have put. After that, you need to put address. Suppose I want to write data into the into this second location. Okay, so I will put sorry, I will put address onto this address lines. This address 010. Okay, then assert a valid write signal. As soon as I will write assert a write signal, then this data is being written into this location on the selected location. In this way, you can write the data. Similarly, you can read the data also. In case of reading, what you need to do, you need to suppose some data is there already and you want to read the data, then for again you need to insert a valid clock signal, then put a address onto the address bus or address lines. Suppose you have put again the same address and activate a read signal. Then whatever the data is stored there already, that will come out to data outline. In this way, the reading and writing operation will be done. So this is what we call as write operation in memory. This is what we call as write operation. We are writing the data. Write operation. Okay, this is what we call as write operation. Similarly, you can have read operations. Okay. Similarly, you have read operation. In this case, if write bar is 0 and read bar is 1, then depending upon the case addresses, your data out, let's say, will get the value of mem location. जो भी specified, the specified memory location that you have here, the same memory location data will come at data. Okay, so these two are the two operations that we need to perform with the memory. So this is the working of a simple random access memory. Okay, how it works, what is the concept, how you can create. So this is the main concept of the capacity. Nowadays we are working with GB, TB, or you can say PT, PB, sorry, terabyte memories. Okay, 1 terabyte. 1 terabyte means 2 to the power 40 bytes of memory. 1 petabytes means 2 to the power 50 bytes of memory. So it's like this. huh? Bytes, then 1 kilobytes, 1 kilobytes, 1 MB, megabytes, 1 gigabytes, 1 terabytes, 1 petabytes. Okay, but the fundamental is bits. 1 bit. 8 bits joined together, 1 byte. Several bytes, 1024 bytes joined together, 1 kilobyte. Then 2 to the power 10 kilobyte joined together, 1 megabyte. So this is where the memory capacity keeps on increasing and increasing. But still it is referred as M into N, total capacity. Okay. So after understanding this concept, let us start designing the memory and let's see how can we do that. Okay, using this concept, right? RAM designing. RAM designing using behavioral style of modeling. So this time I have already created a program for you. Let me just explain it so that you will find out. Suppose so these library you need to install. Apart from that, you have seen that I have included one more library over here. So this is a new library that I have included. Name you can whatever you want. Suppose I have written the name as entity RAM is port clock. Then this is a WE signal. You can create WE or write enable, or you can create a separate WR comma RD. Okay, write and read signal. Similarly, there is an address lines. These address lines, let's say we have created and we have made it 2 down to 0 because in our case these address lines are of 3 bits. So let's say I should write in std underscore logic underscore vector 2 down to 0. Similarly, data in type std underscore logic, data out type std underscore logic underscore vector 7 down to 0. There is a one clock signal, and you can also create one reset signal similar to clock. Let's write it over here itself, RST. Okay, the same entity I have created for this RAM, which we have discussed, right? 8 data lines, 8 input data lines, output data lines, 3-bit address lines. What I have created over here, 3-bit address lines, then read bar and write bar, yeah, read and write signals, and clock and reset. Both are of inputs. Entity and entity RAM. Okay, this is my entity has been created. Now, architecture behavior of, you can write RAM underscore arc. Just we have followed the same nomenclature in every program of ours. So we'll do the same thing over here also. Architecture RAM underscore arc of RAM is. This is a very new concept that you need to understand. Very important, and you need to understand this concept. What I did there actually. So in this discussion, if you understanding, if you are learning, then you can find out that I have written over that we have created a variable which should look like a memory. Look like a memory means it should have the capacity that it can it should be of 8 into 8 type. This type of variable I want. M into N type. Okay, this type of variable I need to create means I need to create a array variable over here. Means every, suppose this is array, and each array, first of all, this is an 8-bit, you can say this is an 8 array. There are 8 locations, and every location can store 8-bit of data. So variable which can have this array type of uh, nature. Okay, so for that VSDL, I have already told you also there are some enumerated type of data types which can be generated. And for that, I need to create a keyword. I need to use a keyword type ram type. The name of the variable is, let's say, ram type. Okay, type, or you can put mem. Type mem is array 0 to 7, means there are 7 locations. Array means I want to create an 8 array, and every location can store 8 bit of data. So this is an 8 into 8 logic. 8 locations. Array means locations, and every location can store 8 bit of data. So I have created a data type of mem type. Okay, and I am creating a variable over here. Let's say, or you should write, okay, I am creating a variable over here of ram type. This is the name of the data type, let's say, and I have created a signal mem of ram type. Now this mem is an array variable. This mem is an array variable. Okay, of this type. It can store 8 bit of data and having 8 locations. Is it clear? Any doubt? I hope, I don't think there should any doubt in it. I have created a simple variable, but for that there is a specific type of command is there, or you can say a specific type of arrangement is there. We need to use a keyword type in it. Okay. After that, rest of the things are very simple, just like begin process clock reset, right? If reset equal to 1, then if reset equal to 1, what we want? We want this mem variable or signal, you can say. Then mem gets the value of. Now what should I write? How do I write in it? Okay, so in it we need to write in this manner, like this. You can see over here. I should follow this 0 0 0 0 0 0 4 and 0 0. Yeah, like this, comma. I need to repeat this how many times? 8 times. This is a single location of it, and this location is storing this 8 bit of data. This is another location. Then this is another location. This is another location. So I need to repeat this the same thing 8 times. 1, 2, 3, 4, and so on to 8 times. Okay, but there is a option of, or another option of not doing the same thing, or you can say of doing the same thing is I should write a one keyword others. Others, I should like this others 0 0 0 0 0 0 0, like this. So what it does, it automatically push this data on every location. Okay, so this is a specific type of keyword that you can write in your program. Others implies that 0 0 0 0 0 0. You can do in this manner. Else if this is not true, then else if means else if either you can use rising underscore h. This is also a positive edge triggered clock example, or you can write what we were doing in the previous classes also. You can write if clock equal to 1 and clock tick event. You can any keyword you can or any attribute you can choose. If clock equal to 1 and clock tick event, then what we want, if write equal to 1 and read equal to 0, right? The same thing that we have discussed in previous slide. If write equal to 1 and read equal to 0 inside it, then now over here, what I did, you can see over here, RAM means mem variable. This is RAM memory. This variable specific location means I'm referring, let's say, mem 0. Okay, but gets the value of data. But this depends upon the address. So I should write, I can write like this also, mem address. Mem address gets the value of data. But this cannot, this this can be is only of integer type. But mine is of std underscore logic underscore vector type. So what I am doing over here, basically, I am using a conversion function which is available inside this library to integer. Okay, so let us understand it. If I want to convert a std underscore logic underscore vector into an integer, okay, then I need to use a function to integer. Okay, and write like this: to integer unsigned and name of the variable. The same thing I am doing over here. I am writing to integer. Okay, or you can also write unsigned because it will work on unsigned data itself like this. Okay, unsigned data in. So what it will do, whatever the address you will pass onto this address lines, it will convert that address into its equivalent integer value, refer to that location, and store the data. Okay. Similarly, if this is not going to happen, it will does this and else 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 means if write equal to 0 and read equal to 1. Okay. Or I should write else if only write equal to 0 and read equal to 1, then same thing should be done over this side. Data out gets the value of RAM. Now this is another uh, this is another same thing but which we have written over here. Uh, this is the same thing. You can see I am copying the same thing at this side. Whatever the data that is available at a specified memory location, it should be out. Okay, else null, nothing should be happen. And if similarly, else for should write one more and if, and I should write else null one more for this clock else if, and if, sorry, only two and if is required for this process. After that, and process and ram underscore arc. So, dear students, hope you got this. In this way, you can easily design the memory logic. The important thing that you should note this library and this the creation of this variable, array variable, and the conversion function. Okay, so one conversion function is when you want to convert a binary logic to integer or std underscore logic or vector to integer. Another conversion function is your uh, integer to binary or integer to std underscore logic underscore vector. So these are the standard functions you can say which are available inside the VHDL library. If you remember that I initially told you about the functions in a specific lecture where we have discussed, I have told you that there are two types of functions, standard function and user-defined functions. So, but in that lecture, we have mainly focused on user-defined function, that how can you create your own function and use them. But there are some standard functions are also there. So these are standard functions. Okay, these are standard functions which you can directly utilize in order to create your program shorter programs and effective programs, optimized programs. Okay, is there any doubt in it? So please let me know. Anybody, if you have any doubt, please let me know in it. So, dear student, let me know if there is any doubt. If there is no doubt, we can move forward. I have actually told you the shortcut method of designing this memory. Using this concept, you can design any capacity of memory. Okay. One another method is using this standard function method. Because if you will go uh, by case like this, then you how many cases you need to write? Case 000, case 001, case 010, case 011. You need to write 8 such cases. And for every case, you need to write the same statement, right? Which would be a very lengthier program, cumbersome program. First, you will write for write. First, you will repeat this for write. Then you will repeat for this read. So your program will be of about 200 lines program. Simple memory, which is generally being taught or generally being you can find out at the basic level in the standard books also. But what I told you today is the generalized program for the memory. Using this program and these conversion functions, there is no bound on the capacity of the memory you want to design. Okay, you can design any capacity memory. Just like this is an 8 into 8 memory designing we have learned today. If you want to design 64 into 64 or 1 GB memory, you can do that. Okay, there is no change in the process. The conversion function will work. All these things would work. Okay, you need only change the data in, data out, and address lines. This small program will work for all different types of capacities of memory. Okay, have you understood what I'm trying to convey to you? Right? Fine. Okay, okay, okay. If it is clear, I'm giving an assignment using the same concept. You need to design a room. That's it. In Rome, what would be there? Suppose I want to design a room. In Rome, what would be there? There is no write operation. There would only read operation. There is no data input. There is only data output. There is no write signal. There is only read signal. That is what we called as read only memory. Okay. So, and we are assuming that we have some data already present in this. I hope you can do it easily. Okay, so this is an assignment for you. Similar type of program you need to write, but I am removing the architecture. You need to write your architecture, own architecture. Rest of the things are almost same. Okay, rest of the things are same. Now you are given an assignment to write the logic for this. Okay, I hope you can do. Yes or no? You try, you people try by yourself. If you find any difficulty, then you please let me know. I will explain. But it is very simple. As we have done in the case of RAM, we have performed write and read operations both. In it, you only need to perform the read operation. So I hope you can do it, and there should not be any difficulty for doing this, right? So, dear students, this is all about our memory designing process. A basic level memory designing, I've told you, RAM and ROM. Okay, but there are some other high level memory designings also there. That just because RAM is also we have what we have designed, this is a single port RAM, but there is a dual port RAM also. Similarly, if we'll talk about FIFO designing, then there is a FIFO designing also. Okay, which are having different applications in other types of electronic systems. Okay, so however, these are some specific topics that need to be discussed on case basis, case to case basis, right? But for our course, this is more than enough as far as your knowledge is concerned and your um, uh, requirement as per your course. As you will learn more things in your BTech degree, furthermore, then you will able to understand what I am teaching to you today, what I am telling you today. Then you will definitely need understand more about this in future. Okay, and maybe who knows, you are able to design that complex memories also if you keeps on practicing, learning all these things, right? So this is the topic of memory designing. Okay, a small topic but an interesting topic, right? And we have also understood about the standard functions, standard conversion functions, right? These are the standard conversion functions available in VHDL. This is an example to show you. Okay, fine. So let's start another new topic today also, and I will give you a brief review of it, and later on, if our time permits, okay, we'll focus on implementation and other parts of designing as well. Okay, we'll we'll focus on finite state machines. Okay, finite state machines. This is a very high level topic which would be generally uh, teached in advanced courses at your BTech level. In your digital electronic, this has been taught at the in the last unit, and most time it is just touched upon. Okay, not basically teached in detail. But when we talking about the designing of digital integrated circuits, right, or digital designing systems, there where we can say the whole electronic system design concept relies. This is a very important in order to design the complex systems. Finite the topic of finite state machines. Most of the times in universities, there is a special course on which has been run after digital electronics that name with the name digital advanced digital systems or digital hardware design systems, something like that. And in that, the topic would start from FSM only. The first chapter would be FSM. Okay, the discussion starts with the FSM only itself. Where digital electronics ends, the next advanced digital level concepts comes. So I have been covering this topic for you also because now we are in the last stages of our course. We have only left with 3 4 lectures. So Uh, I'm giving you this advanced topic overview, finite state machine, so that you can develop some sort of projects as well by your own. And most of the research papers, many projects that you will follow, right, in the IEEE or somewhere else, you will see that okay, some finite state machine always there, being there, and some topic has been discussed. Then you will find difficulty, and you say we have been not teased in VHDL this, right? So that's why I will cover this topic for you people so that you can have the understanding, and further whenever it will come across your reading, you will do not find any difficulty, right? So what is a finite state machine? Finite state machine are useful abstraction of sequential circuits. Basically, finite state is machine is nothing. It is the same thing that we have learned. We have learned sequential circuit. A sequential circuits, it is the abstraction of sequential circuits only. That is what we call as finite state machine. We have learned designing the counter. A counter is also a finite state machine. Basically, a state machine means where you can see where we can say there is a present state, there is a next state. We can apply some input. So there should be some logic which will work on this present state and input, our applied input, and generate the outputs according to our requirement, as well as next state. And that next state would be stored inside somewhere inside the flip-flop or somewhere, and it will become a present state for the next set of inputs, so as to generate next set of outputs and next state. So this cycle keeps on repeating, repeating, and repeating and repeating. Okay, just like in counter, if you remember, just like in counter, suppose we have to design an up counter. So in up counter, your present state is 0, 0, 0, 0, but there are no inputs. Let's say your present state is 0, 0, 0. So your next state depends upon the present state. If present state is 0, 0, then the next state should 0, 0, 0, 1, and that 0, 0, 1 become the present state in the next clock cycle. Once 0, 0, 1 would be the present state, the next state should be 0, 1, 0, and after that, that 0, 1, 0 would be the present state. Similarly, it keeps on doing this. Once it reached 1, 1, 1, then 1, 1, 1 would be the what would be the next step? The next step should be 0, 0, 0. It will come to the same position from where it is started. Your simple counter is also a state machine. It is having a present state, it is having a next state. But we have never seen or implemented that in that fashion. Okay. So in general, we can say there are two types of FSMs. One which are without inputs, and one which are but one with which are with inputs. Just like in the case of counter, there are no input, only present state and next state, and next state is the output only. Next state is the output also. Okay, so we can say there are two types of finite state machines. One is called Mure machine, and another is called Mealy machine. Okay, and their outputs, depending upon their outputs, whether they are depending upon the only upon the next state or the present or the mm, present output, or whether they are depending upon the inputs as well as on the present outputs, present state, or you can say depending upon that, these two FSMs has been identified. If we'll talk about Mure machine, so you can see over here in the Mure machine, we have inputs, then we have some uh, this logic, computational logic, you can say some next state logic where where your present state is stored. Depending upon that present state and input, the next state is generated, which is stored inside the register. The next state again will become the present state, and the final output will depend upon the only on this stored present state. Okay, so this type of Murray machine is called as this type of machine is called as Murray machine, where the output is only depend upon the next state. You can say, or you can say the output of this register. Similarly, in Mealy machine, the output depends upon the state of this register as well as the input also at that instant of time. That is what we called as Mealy machine. Okay, have you understood the concept? Let us understand it by taking an example so that you can have some more understanding what I am trying to say to you. Okay, let us start the concept with the simple real life example where you can utilize this concept and in a very simple state diagram, not very much complex. And because you are familiar with this traffic light controllers in day-to-day life, so you can understand what I am trying to convey. I will try to demonstrate this example for you using Murray machine as well as using Mealy FSM, Mealy finite state machine also. Okay, let's say this is a traffic light controller, two-way traffic light controller example. And in two-way traffic light controller, I am assuming that only one traffic light is installed, having three lights, yellow, green, and red, as you can see in the diagram. Okay, generally, when we have when we talk about FSM designing, we should have a specific type of first of all, what we have, we should have a specific type of designing statement that you need to design this. Suppose I have given you a idea or given you have you a statement that you need to design a traffic light controller for two-way signaling. Only this much information is you are having. So from where you should start? You should start from here itself. First of all, you should make a what should you make a you should make a state diagram. Okay, in state diagram you can represent the states with the circles, just like I have represented red, green, or yellow, green, and red lights. These are the states. And in the states, you can identify what are the present state, what are the next state, what are the inputs, what are the outputs. Okay. So let's say this 00 is representing the yellow, 01 is representing the green, okay, and 10 is representing the red. Because there are three states, I need 2 bits, and 11 is nothing. Okay, 11 is nothing. Okay, 11 is nothing. So 00 and 01 and 10, these are the state numbers just for yellow, green, and red. Okay, then this is a slash division, and at the downside, it is representing the outputs. That what should be the output at this present state, what should be the output at this state, what should be the output at this state. Okay, I am assuming that my system is starting from this yellow light. Just I have installed the traffic light and I have um make it on by using a switch. I have to make it on by using a switch. So I make it on. Okay, in the morning I go there. there is a switch and I press on that and traffic light starts. So where should it start? It should start from yellow. Okay. So let's say it start from yellow and presently the present state is yellow, means it is having 0, 0 state. And what should be the upcoming state? The upcoming state means the next state would be green, represented by 0. Is it clear? If it is at a present state, what should be the output? So let's say there are 3 bits for representing the output. For yellow light, there is one for yellow light, another is for green light, and another is for red light. So when it is at yellow state, the yellow light is on, the green light is off, and as well as your red light is off. And the upcoming state would be the green state. Once it is completed its yellow state, it will come to green state after certain interval of time. Let's say 5 seconds, 6 seconds, 10 seconds, 20 seconds. Number of clock cycles that you want to switch. Okay. After that, once it will come to this state, now it is in this state. In this state, the present state is green, representing by 0, 1. And the next upcoming state would be 1, 0, that is red. When it is this is at this state, the yellow light should be off, the green light is on, and the red light is off. Am I right? Again, it should be there for some sort of clock cycles, depending upon the frequency. And after once it is completed that, it will now jump to this state. Now, when it jumps onto this state, the present state becomes red now, that is 1, 0. And the next upcoming state should be 0, 0. Yani means the initial state from where it is started. If there is any state there, it can go to there and then it will come to this state as well. But in traffic light only there are 3 lights we are assuming. There are only 3 states, so it will come to the initial state. Simple as it is. Okay. When it is at this state, the output is this. Yellow, red, green is off and red is on. This is what we call as state diagram. Sometimes the problem of statement may be given in the form of a state diagram directly. Sometimes it is not. You need to create this state diagram by your own mind or on your own logic or your own learnings. Okay, as depending upon your practice and how you have analyzed the situation for creating the system. Okay, right. So that's what this is how I have created a state diagram. Now using this state diagram, I can simply create a table, state table you can say, and I can simply create a state table. Okay, how? Let's say this is my present state and this is my next state. Okay, so present state are represented by 2 bits. So I'm assuming if there are 2 bits, so that means in my system there should be 2 flip-flops are going to use because 1 bit can be stored in 1 flip-flop. So definitely I need two flip-flops to store 2 bits at least. Okay, fine. This is a simple logic. Okay, and these 2 flip-flops help me for storing different states. There are 2 bits. I'm representing the state with the 2 bits. That means 2 flip-flops are required. Okay. So present state is 0, 0, next state is 0, 1, and so on. So like this. So I'm written over here present state and then over here written next state. So depending upon my state diagram, I have created this table. Let's say this is the present state QB Let's say this is flip-flop B, this is flip-flop A, and next state that it is coming up, it is QB plus 1 and QA plus 1. So present state of 2 flip-flops and present state for next 2 flip-flops. Okay, of same flip-flops. If present state 0, 0 as per the diagram, and the next state would be 0, 1. So I have written the same thing 0, 0, 0, 1. And if it is at 0, 1, the next state is 1, 0. Similarly, if it is at 1 0, then its state is 0 0. But what about if it erroneously enter into 1 1 state? We have now not defined over here. Anywhere we have not defined. So if anyhow erroneously it will jump from 1 0 to 1 1 state, or come to that state by any fault, what we have created, that I have written, if anyhow it will jump onto this 1 1 state, it will again come to the 0 0 state only. Okay, so that there should not be any chance of any fault in my machine, because if it will go into 1 1 and I have not specified a specific state where it should go, then it will keep on popping into one state or another state. Means your traffic light keeps on jumping randomly. Sometimes you have seen in these streets also that lights are not working properly. So there should be proper uh, use case for every test inputs, present states. Any should we cannot skip any present state. Okay, so these are my desired present states and desired next states. After that, as per this present state and next state, what I have created yellow light and green light. So in when this is there, when present state is 0 0, yellow light is 1 and green light and red light is off. When present state is 0 1, means your we can say green light is there, so green light is on. When 1 0, that is means red light is there, red light is on. Again, when 1 1 is there, I have told the next state, so at that time yellow light should on. Okay, this is an erroneous state. If this state comes, then only this would happen. So I have created this present state, next state, and okay. What I need to identify actually, what should be the input logic and what should be the output logic of these flip-flops. These two flip-flops that I have for which the I have talking about, this is the present state and this is the next state. Okay, I want to know what is the input logic and what would be the output. Means, as per this diagram, I am going to use these flip-flops. I am talking about present state, next state, present state, next state, present state, next state. But what should be the input logic and what should be the output logic, so that I can combine over there, so that an FSM should be created. To identify the input to this flip-flops, I need to use the combination of present and state and compare that combination with the transition table of, you can say, that flip-flop which I am going to use. You can choose any flip-flop, whatever you want. It may be D, T, J, K, Q, whatever, SR, any flip-flop you can choose. But depending upon the scenario or given in the question or as per the requirement, you can choose your flip-flop and follow the, try to map the present and next state situation with the transition table of the uh, particular flip-flop. Okay, so if I would compare the transition, these states with the transition table of, suppose I am using the D flip-flops, two D flip-flops are there. So, and if I want to identify what should be the inputs of these flip-flops, so to identify the input logic to these flip-flops, I should have to compare the this QB and QB plus one for identifying the input DB. So, if you remember that the D flip-flop, the transition table for D flip-flop is that Qn plus 1 equal to D. Means in D flip-flop, whatever available at the input, the same is available at the output, because it is sometimes it is called as transparent latch or transparent D flip-flop. Whatever the value will apply at the input, it will available at the output. Okay, so in case of D flip-flops, then whatever may be the present state, output So that's why I have copied the same thing over here. Similarly, for this also, second flip-flop, I have copied the same thing over. Now I have got logic for my D flip-flops. And this is the transition table, state table, which I have created. Okay. Now to logic DBDA, right? I need to create a, this is the input logic, D and DB. And for output logic means for input logic, I have to identify DA and DB, what should be at my input. And for output logic, I need to identify lights. I need to identify this combinatorial logic. I need to identify outputs logic also. Yellow light, green light, and all of these, all of these things depends upon this present state, right? So if you see closely watch, I have created a K map, two variable K map, which is representing DB input, and for this DB, this QB and QA are the inputs. Okay, QB and QA are the inputs. So you can see for 0, 0, 0, 1, 1, 0, and 1, 1, the output is 1 only at 0, 1 position. Accordingly, I have created this logic. Similarly, for DA also, the output is 1 at 0, 0. I have created this over here, this also. Similarly, if I will see yellow light, for yellow light, QB, QA, the output is 1 for 0, 0. Similar output is 1 for 0, 0 and 1, 1. So there are two ways. Similarly, for green light, this, and similarly for red light, this. Very simple and straightforward, you can say, observation over here. You can see now using this information, these Boolean expression, you can create your state machine diagram. Okay, FSM state machine diagram. In FSM state machine diagram, what you need to do? This is the FSM state machine diagram. You can see over here. In it, first of all, I need to. You can see over here. First of all, I need to write DB and DA flip flop. This is flip flop A and this is flip flop B. I have identified DB and DA. Okay. This is the input logic, next state logic, you can say, yeah, input combinatorial logic, and this is the output combinatorial logic that I have created, output logic, and these are the outputs. This is the present state, and these are the present state will become the next state, and so on, so on, and so on, like this. Okay, using this information, that what should be the connect, just like at DB, QB bar and QA, I have connected. So at DB, QB bar, this is QB bar, and QA, this is QA, ANDed together, and they are connected as an input to DB. This is a clock signal. Similarly, at DA, QB bar and QA bar is connected. That is QB bar and QA bar is connected at DA. This becomes the input logic. Similarly, at output logic, directly you can see YL. This is nothing but this is a XOR gate. XNOR gate. This is XOR gate in which QB and QA are input. Similarly for green light and similarly for red. This is your state machine, complete state machine. If you'll implement this inside the FPGA logic or you will create an IC, this IC can be utilized anywhere inside any traffic light control system where uh, you need two-way traffic light control. Okay, and in it you can see the output, your final output is only depending upon your states of the flip-flops, present states of the flip-flops. Am I right? So that's why this is FSM, traffic light FSM is a Murray FSM. Your output is only depending upon this, not input logic. There is no input is coming from somewhere or somewhere else. Okay, so this is a simple Murray FSM. Dear students, if you have any doubt in it, please let me know. Please confirm. Very important discussion, a very important topic. I have tried to make it as simple as possible for you so you have to understand. But if you miss something, if you need explanation in any of this part, please let me know. Please confirm fast. And if there is not any doubt, then it's okay. You keep check this video, repeat this video by using the recording and try to understand and try and go to the internet or go check your book for your digital electronics, whatever you are referring, and try to identify this topic. And whatever I have told you, try to match that topic, and start learning FSM. Very important in terms of designing complex systems. Okay, students, if you have any query, you may WhatsApp me also. You can write an email me also. Even okay, whatever you have doubts. For today's discussion, I'm closing this session over here. Okay, tomorrow we will discuss one more part of it. That is what it is called the Mire state diagram, where I will be inferring one sensor in it, some input in it, and how this state diagram changes accordingly. And finally, we'll see what would happen in the state table, how it changes, and then how your final FSM state diagram is also gets changes. Okay, we'll see that tomorrow by tomorrow. Till that, if you have any doubt, please let me know, or otherwise, we will be closing the session for today. Yes, please. Hmm. Yes, I can help you out. You can share your screen. Dr. Tukur, please help a student to share his screen. I'm stop sharing my screen. Not now. Yes, yes, now it is. It is. It is. It is. Can you first me show? Can you go into the Mux VSD program first? Okay, yeah. Show me VSD program. Okay. You have created IO. Okay. First of all, changes this IO. Go on top. Go on top. Go on top. Mhm. Go on top. First, you will close this simulation. Close this simulation. Go on to this cross क्वेश्चन मार्क जहाँ पे बना हुआ है वहाँ पे क्रॉस पे जाइए और उसे क्लोज कर दीजिए. ऊपर 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 ब्लू विंडो के पास. हाँ हाँ क्लोज दिस. जस्ट अ सेकंड.